On the 3rd of June 1998, a German high-speed train was cruising at 124 miles an hour when a single wheel underneath it quietly split apart. 9 seconds later, 101 people were dead. Here's the twist nobody expects. That wheel didn't fail because the train lacked steering. It failed because of the exact same design that lets a 400-ton train round a curve without a steering wheel, a pedal, or a driver touching anything but the throttle and the brake. That trade-off is one of engineering's oldest, quietly brilliant compromises, and on a Tuesday morning in Lower Saxony, it turned deadly. Start with the obvious question. Why build a machine this way at all? A car has 4 wheels that can each spin at a different speed and each turn independently. That's exactly what lets it steer. A train's wheels are nothing like that. 2 wheels on a train are bolted rigidly to a single steel axle. Both wheels spin at the identical speed, always, whether the train is going dead straight or curving hard to the left. There's no differential gear splitting speed unevenly between the two sides the way there is under a car. On paper, that sounds like a disaster waiting to happen, because on any curve, the outer rail is physically longer than the inner rail. The outside wheel has more ground to cover in the same single rotation. Lock both wheels to one speed, and something has to give. This is where the shape of the wheel does something almost nobody notices from a platform. The tread isn't flat. It's slightly tapered, wider near the flange, and narrower toward the outer edge, like a cone laid on its side. When the axle drifts toward the outside of a curve, the outer wheel starts rolling on the fatter part of that cone. Bigger effective diameter. The inner wheel rolls on the thinner part, smaller diameter. Same rotational speed, different rolling diameters, and the outer wheel quietly covers more ground per turn without spinning any faster. The axle steers itself sideways into position through pure geometry. No motors, no linkages, no input from the driver at all. That steel flange riding the inside edge of each wheel almost never touches the rail. It's the backup, not the main event. Most of the time, the conical taper alone keeps the wheel set centered, gently swaying in tiny corrections engineers call hunting, a self-steering oscillation that's harmless at low speed. Push the train too fast though, or let the wheel profile wear into the wrong shape, and that gentle sway can turn into a violent side-to-side shudder called hunting instability. That's the phenomenon that sets the real speed ceiling for a given wheel and track combination, long before the engine itself runs out of power. None of that explains Escadé on its own. The ice that derailed there wasn't running an ordinary solid wheel. It carried a rubber-sprung design, a steel tire wrapped around rubber blocks instead of one forged piece of steel, built to smooth out vibration for passenger comfort. Every rotation flexed that rubber layer hundreds of thousands of times a day. Over roughly 4 years and 1.8 million kilometers, one of those tires quietly grew a fatigue crack that routine flashlight inspections never caught. When it finally let go at 124 miles an hour, the broken tire punched through the floor of the passenger car, got dragged into a track switch, and forced the train's wheels down 2 separate paths at once. The exact flexibility engineers had added for comfort was the same mechanism that eventually cracked. That trade-off was never free, and Escadé is the reason high-speed railroads went back to solid, monoblock wheels almost everywhere and started requiring ultrasonic crack detection instead of a technician with a flashlight. Railroads didn't stumble onto the conical wheel by accident either. Early 19th century engineers experimented with flat wheels, geared steering linkages, even wheels adjustable by hand for different curves, before George Stephenson's workshop settled on the conical, flanged profile that's still standard today. There was also a fight over gauge itself, the exact distance between the two rails, with Isambard Kingdom Brunel's Great Western Railway running a wider 7-foot gauge in England, while Stephenson's narrower 4-foot 8.5-inch gauge spread everywhere else. Parliament eventually forced the whole country onto Stephenson's number in 1846, and that width, oddly specific as it looks on paper, is still what almost every wheel cone on Earth is engineered around today. So if the wheels handle steering themselves, what's actually underneath a passenger car keeping everything aligned? The answer is the bogie, sometimes called a truck, a small rolling frame carrying 2 or 3 axles under each end of a rail car. The bogie pivots independently from the car body riding above it. Without it, a long rigid railcar couldn't make it around a normal curve at all, because the front and rear axle sets would try to steer in 2 different directions simultaneously. The bogie is what lets a 100-foot passenger coach snake through curves that a single rigid frame that long could never survive, while the body sitting on top barely registers that a curve happened. Even the sharpest curves railroads ever dealt with weren't solved by adding steering. Narrow-gauge mountain lines carved into places like the old Colorado silver routes or the Welsh slate quarries solved tight switchbacks by shrinking everything instead. Narrower gauge, shorter wheelbases, tighter bogies. The same self-steering geometry survived curves a standard gauge train would derail on. Entire branch lines got built to those tighter specs, ran their short, profitable lives hauling ore or slate, then got abandoned outright once trucks and highways took the freight. Walk certain mountainsides today and the rusted rails are still there, curling through forest that hasn't seen a train in decades. A handful of railroads did try to cheat this system with real mechanical steering. Articulated Talgo trains out of Spain use independently rotating wheels on each side of an axle instead of one rigid shaft, letting each wheel spin at its own natural speed and steering the axle actively rather than relying purely on cone geometry. Tilting trains like the Pendolino go a different route, using hydraulics to lean the car body into a curve the way a motorcycle leans, letting passengers ride faster through a bend without the sideways lurch. But the wheels underneath are still doing the same conical, driver-free self-steering they've done since Stephenson's era. Nobody has ever put a functional steering wheel in a locomotive cab because there has never been anything for a driver to steer. The rails did that job before diesel engines or electric motors even existed. What the driver actually controls is speed and traction, and both turn out to be their own quietly demanding skill. Push too hard on the throttle and a locomotive's driving wheels can simply spin in place against the rail, exactly like a car tire on ice, because steel on steel offers surprisingly little grip once you overload it. Engineers fight that with sand, literally, dribbling fine sand from domes onto the rail ahead of the wheel to boost friction for a few critical feet when starting a heavy train or climbing a grade. Braking runs into the same problem in reverse. Lock the wheels under hard braking and you get a flat spot ground into the tread almost instantly, the exact defect that triggers hunting instability at a lower speed than a healthy wheel would allow. That's why modern trains use wheel slip protection systems, quietly releasing and reapplying the brakes dozens of times a second, the same basic idea as anti-lock brakes in a car, just scaled up to hundreds of tons. It's worth asking the obvious follow-up too. If cars solve this with a differential, why not just bolt one onto a train? Engineers have actually tried, going back over a century, and the honest answer is weight and reliability. A differential capable of handling the torque of a locomotive hauling 10,000 tons would be enormous, expensive, and one more complex part that could fail at the worst possible moment. Modern light rail and trams sometimes do use independently rotating wheels for exactly this reason, since they run shorter, lighter, more tightly curved routes where the extra complexity pays for itself. Heavy mainline rail almost never bothers. The conical wheel does the job for free, using nothing but the shape a 19th century workshop gave it. Maglev trains sidestep the whole argument in the opposite direction. Japan's experimental SC Maglev has run tests north of 370 miles an hour without ever touching the guideway it floats above, held a few inches clear by magnetic repulsion instead of steel wheels on steel rail. There's no conical tread doing quiet geometry work because there's no wheel at all. Guidance comes from the magnetic field itself, actively adjusted thousands of times a second by onboard computers. It's a completely different answer to the same underlying question. Wheeled rail solved steering with pure shape a century and a half ago. Maglev solved it by removing contact with the ground entirely. Neither one needed a driver's hands on anything resembling a wheel. Subways push the conical wheel to its actual breaking point because city tunnels force curves far tighter than any mainline railroad would ever tolerate. Beyond a certain radius, the self-steering geometry simply runs out of taper to work with, and the flange starts scraping the rail on every pass instead of riding clear of it. That's where engineers add a second rail, a guardrail bolted just inside the running rail through the sharpest curves, which physically catches the back of the opposite wheel's flange and stops it from climbing up and over the top of the rail during the exact moment the conical taper alone can't hold the geometry together. It's a purely mechanical failsafe for a purely mechanical steering system, and most riders have stood directly above one without ever noticing the extra strip of steel doing that work beneath their feet. A modern freight train can also stretch 1.5 miles long, and slack action, the small gaps between couplers, means the front of that train can be accelerating while the rear is still braking, forces an engineer has to feel through the cab rather than see. Conductors and car inspectors walk entire trains, checking wheel flanges for flat spots, thin treads, and hairline cracks that a quick visual pass can miss, the exact category of failure that brought down the Escadé train. Some yards still use the old trick, tapping a hammer against the rim and listening for the wrong pitch. A dull thud instead of a clean ring means a hidden crack. Freight yards run a bigger version of that same maintenance grind at industrial scale, in wheel shops called truing facilities that remachine the tread on worn wheel sets. Shaving the profile back to the correct taper after months of running has flattened it slightly. Skip that maintenance and the same hunting instability that caps a passenger train's top speed shows up sooner and rougher on freight cars that already run heavier and slower with far less margin for error. Dispatchers and track maintenance crews carry a quieter piece of this same responsibility. Rail itself wears unevenly under the constant sideways load of thousands of wheel cones, steering themselves through the same curves day after day. So railroads run specialized grinding trains that shave the railhead back into the exact profile the wheel taper expects. Get that profile wrong, even by a fraction of a degree, and the whole self-steering relationship between wheel and rail starts to degrade, quietly increasing wear on both sides long before anyone notices a problem from inside the cab. It's maintenance most passengers will never see and never think to ask about, keeping a 19th century idea working correctly at 21st century speeds. So the honest answer to why trains don't have steering wheels isn't that nobody thought of it. The wheel itself already is the steering mechanism, shaped steel doing invisible geometry no driver could replicate by hand at highway speed, let alone at 124 miles an hour. The system is elegant enough to move a loaded freight train 1,000 miles without one manual correction, and fragile enough that a single hairline crack, missed by a routine inspection, ended 101, lives in under 10 seconds outside Escadé. Next time you watch a train glide through a curve with nobody visibly steering it, look again. You're watching a 19th century idea still quietly doing a job nothing newer has managed to do better.